Okay, so what the empirical rule tells us is that within one standard deviation of either side of the mean, 68% of the data lies. Within two standard deviations of either side of the mean, 95% of your data lies. And within three standard deviations of the mean, 99.7% of the data lies. So, does all the data lie within three standard deviations of the mean? No, we've got that 0.3% unaccounted for right now, don't we? Where is it? It's past the three standard deviations on either side.
Miss Wilby, I think one of them I tried to he was asking if it goes all the way, so less than 5.3 hours.
It becomes insignificant.
Right, it does.
Oh, so
at a certain point, it does become insignificant.
So you wouldn't add 0.15 to it?
I'll get to that question in a minute. Within many standard deviations outside of the mean, you're right, it does become insignificant. Up to, what do we have on here? 3.5 standard deviations of the mean. It's just about everything. All right, so let's look at, this was number 1 on your learning task yesterday. And didn't y'all put these answers up on the board during class?
Yes,
Did somebody log them? Okay, so if we look at this, you can barely see, do you see the normal curve going through my histogram? Okay, so the normal curve is going through the midpoints of each of the bars of the histogram.
I didn't notice that.
And so I tried to draw it on the board because your copy was really hard to see, and that's the best I could do when I drew it on the board. And also your copy, you couldn't see the pretty colors, so I drew that on the board for you yesterday also. So some things you could have said that the two graphs have the same peak, that the normal curve cuts through the midpoints of each bar. Did you guys have anything else to add?
They curve similarly.
They have a similar shape. Okay, one's just a curve and one's made out of rectangular boxes.
Good luck trying to make a curve.
But what if we took these rectangular boxes and changed the width down here and made the width smaller and smaller and smaller and smaller and smaller? What would happen?
There'd be less deviation.
It would look more and more and more like the curve, wouldn't it? Okay.
Oh.
All right. So you were estimating here what the standard deviations were. So the taller the curve, the smaller the standard deviation, because the tighter the data is to the mean. The tighter the data is to the mean, the taller your curve. All right? Now,
2.2.
on the second one, did you notice that every one of the curves looked similar? They were similar in shape and in size. They had just been shifted. So the standard deviation should have remained constant, but what changed was the way we shift a normal curve is we shift the mean. So as the mean gets smaller, it moves further over to the left. As the mean gets larger, it moves to the right. Okay? Makes sense? All right, and that's basically what was summarized down here for you. Is the mean moves the curve left and right. The smaller values move the curve to the left. The standard deviation affects the width and therefore the height of the curve. So the more narrow the curve, the smaller its standard deviation, and the closer the fit of the data is to the mean.
Wow.
All right, continuous probability distributions. So we kind of jumped over discrete probability distributions. We talked about them a little bit in terms of expected value, but that was about it. Discrete is what we use, like if we were playing a game and we could get a 1, a 2, a 3, a 4, a 5, or 6 on a dice. That would give us our discrete probability. But continuous would be something that's measurable. All right? So these were our notes on continuous probability distributions. Has the following properties. So once we have a normal distribution, then the mean, median, mode are all equal. It is bell-shaped. So when you hear the word bell curve, what are people talking about? A normal curve, aren't they? It's bell-shaped and symmetric about the mean. The total area under the curve is 1. It approaches, but it never touches the x-axis and extends farther and farther away as it extends farther from the mean. And then the points at which the curve changes from curving upward to curving downward are called inflection points. So do you see how it kind of goes from up to going down? See how it's doing that right here at this point? And that inflection point is occurring plus or minus 1 standard deviation from the mean. So mu is representing the mean of the data, and theta is representing standard deviation. Okay, so the empirical rule says that 68% of the data lies within 1 plus or minus 1 standard deviation of the mean. And because it's symmetric, and that's 68% of the data, this section from 0
34%.
1 standard deviation to the left would be 34%. 1 standard deviation to the right of the mean would be another 34%. And we have to use these to add them up when we're using the empirical rule to estimate. Now, where did these numbers come from?
95 minus 68 divided by 2.
Excellent. You're right on the money, Brian. So to get these two areas, we would do 95 minus the 68 divided by 2. And then to get between 2 and 3 standard deviations, we would do 99.7 minus the 95 divided by 2. And then to get way out here, the part that's not even registered, we would do 100% minus 99.7% divided by 2 to get the area under the curve that is more than 3 standard deviations or less than negative 3 standard deviations from the mean.
It was just point delta zero.
Okay, so in this particular,
Wait, now, Miss Woody, why is it point delta 5 when it was?
okay, because 0.3%,
Oh, that'd be point.
it went from percent to just the decimal. This is the probability. Probability we write as a decimal. And then up above, they're talking about the percent of the data that falls within that range.
Okay.
So it's addressing it two ways. One, the percent of the data. Two, the probability that something actually does fall there. All right, so estimate the probability that a randomly chosen adult has an IQ between 85 and 145 if the mean IQ is 100 and the standard deviation is 15. Now, you definitely could do this without drawing a picture. But I drew the picture. The mean is 100. So if I went left 1, that would be 85. Left 2 standard deviations, I'd be down to 70. Left 3 standard deviations, so negative 3 standard deviations, I'd be down to 55. Positive 1 standard deviation, I'd be up to 115. Positive 2, 130. Positive 3, 145. So what this is this range, 85 to 145, is 1 standard deviation to the left and 3 to the right. So if I'm finding that probability, if I take the area under the curve and add up those areas, that gives me the probability that it falls within that range. Does that make sense?
Okay, so let's summarize the empirical rule one more time. If we have a normal distribution with a mean of mu, and we've been talking about mu, mu means the average for the entire population. So this is our symbol for mu. With the standard deviation, okay, you can approximate the areas under the curve as follows. Within 1 standard deviation of either direction is 68%. So once again, that is because it's symmetric, it's dividing up into 0.34 and 0.34. Within 2 standard deviations of the mean, we have 95% of our data lies. Within 3 standard deviations of the mean, 99.7% of the data lies. Okay. Also, we talked about this inflection point where it goes from curving up to curving down. Do you see how the change happens right here? This inflection point. The inflection point occurs 1 standard deviation on either side of the mean. So if we look at the back, it asks us to give us the mean and the standard deviation. So if we look at the first problem, well, it looks like the mean of the data is right here. So the mean occurs at about, we're going to estimate here, 3.5. Now, the inflection points are noted for us. And if we look, these inflection points occur at 2 and at 5. So how far away is that from the mean? Because that would give us approximately 1 standard deviation. So that distance is about 1.5. All right, take just a minute and see if you can do the next 2 on your own. Okay, on the second one, if we look, the mean is still approximately the same position, 3.5, but the inflection points are somewhere around in there. Maybe at the 0.5 range, maybe a little even closer. So you could say, estimate the standard deviation to be about 1 unit. I'm really struggling drawing a straight line down on this one. So about 1 unit away. On this one, we see that the mean has changed. It has shifted to the left, and the mean is now at approximately 1.5. And that standard deviation is approximately the same as the previous one, so it's about 1 again. So if the standard deviation is the same, that height of the curve looks the same. And when the mean shifts, it shifts left or right. Okay, so in B, which normal curve has a greater mean? So let's look at it. The mean would be here. The mean would be here. That's where our line of symmetry can be drawn. So I would say that A has the greater mean. The mean is approximately 15. Which normal curve has a greater standard deviation? So this one, which one has the larger spread? Well, we can look at the picture, and without calculating anything, we can see that B is more stretched out. It has a greater spread. And so if we approximated the inflection point about right here, we can see that that one standard deviation would be about 3. So those are just approximations of the mean and the standard deviation. C, find the line of symmetry, therefore identify the mean. So let's read this. It's talking about the diameters of fully grown white oak trees are normally distributed. The normal curve shown below represents this distribution. What is the mean diameter of a fully grown white oak tree? And estimate the standard deviation. So the mean appears to be right around 3.5. Okay, that's where I would approximate the mean to be. And the standard deviation, let's see. So we want to show kind of where that curving down to curving up change happens. Maybe around there, maybe around here. So you could say the standard deviation was approximately 0.25 feet. And that's how we would approximate those. Okay, for homework tonight, you have a worksheet where you have some problems, many that are similar to the U-try that we went through earlier in the video. So you guys work together in class, and I'm going to be back tomorrow to answer any questions you might have on these continuous probability distributions using the empirical rule.